Let's start in the back row. So again, demonstrations will start 7:40, okay, directly after class. If you have a good feeling about the state of affairs concerning your program, then I suggest that you sign up for the Tuesday, okay, for a Tuesday time slot. If it happens to be that your program still crashes, I mean, at 7:40 next Tuesday, then you can swap to a Thursday time slot, okay? So again, we start at 7:40 right after class. The second project, again, is quite expensive to compute the results, right? As you know, the Hardy method requires some time to compute good pictures when you use many sample points. So be ready to show to me some snapshots, captured images, right, where you have the results. This picture was generated using so-and-so many samples, this type of distribution, and so forth, okay? And then toward the end, I would like to see how you actually run your program. Okay, what's the input, what's the output file, and what are the parameters that you read in from the file or that you can type in. Okay, so I see the process. On Tuesday, we start 7:40, take 5-minute increments. Okay, so the first one who signs up, 7:40, then 7:45, 7:50, and so forth. So also last questions. If you have any questions remaining regarding the second assignment, ask me now. There was one question coming to me by email. Who asked the question? Okay, Mr. Hay, please.
About how many random scatter points are you expecting for Hardy's method?
Okay, so, and the question had a twist to it, right? The question said, Bernd, Hardy takes a long time when I use 64 cubed samples. But the 64 cubed samples, that number is not the number of samples to use, but the 64 cubed is, say, the output mesh onto which you approximate, onto which you sample for rendering. Okay, so this is a scenario, just to make that clear. Obviously, I didn't make it clear. So if we want to approximate the temperature in this room, your input data set might be, I mean, you might have a Volvis.org data set that is of 512, 512, 512 size. Huh? All right. Then you just randomly pick a subset of these Cartesian mesh points. And the number of points should, of course, not be 512 cubed. That would take forever. But you try to reconstruct this temperature field in this room using 10 points, using 100 points, using 1,000 points. Maybe more if you do parallel computing, okay? So, but ultimately, once you have your coefficients for the Hardy function says h at the point x, y, z, then you can evaluate this Hardy function, h, at any point on your evaluation mesh, right? So for rendering later on, you want to, of course, use a nice Cartesian mesh to make your raycast image or to have your cut plane go through it, and then you can use any resolution that you want. 64 cubed or 128 cubed or 512 cubed, whatever. Okay, but again, the time to compute the coefficients in this Hardy formula, in the Hardy expansion, that depends on the number of samples that you take from the zoom. Right? So again, if you have this temperature in the zoom, you take 100 random locations where you have the temperature, boop, and then you feed those sample values, Fi, into the right-hand side on that linear system. But you have, if you pick 100 points, then you have to use 100 by 100 matrix. And this matrix is an ugly matrix because it has no structure and it's full-blown, and etc., etc. And I said at least you can make the matrix a little bit nicer by fooling around with this parameter called this R squared. Okay, the R squared should be chosen relatively large with respect to the sampling density and the size of the room. Okay, so that's something for you to experiment with. Is it clear that the output mesh resolution does not dictate the computation time? The computation time is dictated by the number of samples you feed into it. Okay? And so how many to use? You use as many as you're willing to wait for, right? I mean, if 1,000 samples requires an hour to compute, well, then 1,000 is probably your limit. And so again, you want to reconstruct a temperature field, a velocity magnitude field, a grayscale density of a skull, choose a few. And of course, you want to start with something simple. So your initial data set is just x squared plus y squared plus z squared on the unit cube, 0, 1, 0, 1, 0, 1. where you see you can reconstruct something that has spherical contours. I want to see that, so then I have some confidence that your implementation might be correct, right? Because it will be long more than 10 lines, and any program over 10 lines has errors. Right? My program, so. It's all clear, right? Okay. Any other questions about Project 2? Shoot.
So would it be acceptable to use the volume raycaster from the previous assignment as opposed to implementing slicing?
I want slicing.
Okay, you want slicing too.
If you, I want to see slicing, okay, but the slicing is a very primitive form of slicing. If you evaluate your final approximating function on a Cartesian mesh, then I only want you to slice in x direction, in y direction, and in z direction. Boom. The simplest slicing there is. Right? Constant index slicing, right? I equals 0, I equals 1, j equals 0, j equals 1, k equals 0, k, and so forth. And then go row shading in the cutting in those slicing planes. Yes, of course, if you have a working ray tracer and you want to get some additional credit, do that. Okay, then you also can ray trace these things or raycast these things. Can I give a lot of additional credit for that? Probably not, because I assume, of course, that you have a working ray caster lying around from your first project. But yes, of course, if you have there's some additional effort, so I will value that. Okay. But the thing that I want to see is a slicer, because I do not trust raycast images as much as I trust sliced plane images. Okay. Raycast images more and more gets averaged. Everything looks good. Make sense? Again, if you want to do the cut plane thing in a more arbitrary way, arbitrary cut planes, multiple cut planes, transparent cut planes, and whatnot, by all means do that, and you get some additional credit for that. Okay. Shoot.
I remember when you first said about picking R squared, you said something about making it diagonally dominant.
The question is that even possible?
Yeah.
Yeah.
I looked up the definition on Wikipedia, and I don't think it is possible to make it diagonally dominant.
Okay. So diagonally dominant matrices are helpful, even necessary, for certain iterative methods to solve large linear systems. The diagonal dominance is not so important if you use a direct method to invert something. Okay, but anyway, this is something I want you to look into. Okay. So if you think that you can make it diagonal dominant for certain things, do that. And see what happens when, whatever method you use, things go bad, okay? When you use bad R-squared values.
Okay. Also, I think the Hardy matrix, is it symmetric?
The Hardy matrix you get is not symmetric. No.
Okay.
It's in general not diagonal dominant, it's not symmetric, it's not block structured, it's not banded, it is nothing of those nice properties. It doesn't have any of those nice properties.
I thought that there would be symmetric.
Is it? Because we have distance from I to j, distance from j to I?
Yeah.
I have to think about that, if that's really true. Is it?
I think it is.
We have the square root. It's r squared plus distance from that point to an I sample, or versus the other way around, right?
If you look at these, it's like a really, it's from
x. It's from x to sample and from sample to x. So
it's symmetric.
Should be.
So that gives us some tricks to do.
At least gives you maybe symmetry, yeah. So it should give you a symmetry, but it doesn't have any big chunk of zeros, because all these distances and this R-squared stuff is larger than 0, so it doesn't have a big block of zeros. It has not, it's not tridiagonal or bent diagonal, it's not block structured, nothing like that. Okay, but at least with the symmetry you can do something. And you can do something nice with iteration if you make it diagonally dominant.
All right.
Should.
I don't think it's possible to make it diagonally dominant, at least by Wikipedia's definition, and that the magnitude of the diagonal entry has to be greater than the sum of the magnitudes of all the other entries in that row.
Yes.
And since the the entry in the diagonal is guaranteed to be the
you got it, because I mean the lowest threshold is the distance could be 0 in the ideal setting, but then you still have all the square root of r squared in the entire row, and therefore because you have the square root of r squared in the middle, then you have square root of r squared in all the other ones, at least even larger entries. So therefore you can not really achieve it, right? You got it.
Oh yeah.
Yeah, that's why that one is better. And you do both, right?
Yeah.
All right, great that you think at that level. That's cool. When I learned this stuff, I had to look at the behavior of these basis functions and what all of that means, and really look at the individual basis function popping up there and characteristics of that basis function, blah, blah, blah. Radial basis functions, actually entire books written on the topic on radial basis functions. These things are all radial basis functions-based methods for approximation. So what comes next? I take it that there are no more questions on the second project. So then we talk about this issue of mesh-based or triangle-based, more specifically triangle-based scatter data approximants. And so our current goal, triangle-based scatter data approximants, scatter data approximation or approximants, approx. That's a topic. So we only have to understand what's going on in the neighborhood of a vertex that is shared by multiple triangles and along the edge that is shared of two triangles. One smooth approximation. And that really translates into only two types of conditions: smoothness at the vertices and smoothness along the edges. Smoothness around or at shared vertices, and smoothness across or along edges. Smoothness along a shared edge. There's only one, at most one, a shared edge. So sketch x, y, and function value. So say if we have, I only want to draw it for this, we have three triangle patches coming together at one vertex, then we would like these three patches to come together in such a way that there's one unique 3 times the same normal, or the 3 times the same gradient, right? So when I make a rendering of this of these 3 patches that live over this domain space, 3 triangles, then these 3 triangular patches, curved in space, come together at one shared vertex that can be of arbitrary valence. In this example, I've drawn 3 patches coming together, but in general, there can be an arbitrary number of the triangles, of course, coming together, right? Arbitrary triangulation. And where these patches come together, of course, for rendering purposes and whatnot, we would like to make sure that there's one unique normal. So when you compute the normal for this guy, for that guy, for that guy, at this shared corner, they all have the same. And of course, the other condition is it's at most 2 triangles sharing an edge. So we want also this normal to be the same along the edge of 2 neighbor triangles. So the other situation is this situation. We have the shared edge, and along this edge, we would like to have a smooth variation of tangent plane, or this is called the cross derivative, right? There is the same derivative, the same slope when I move along this shared edge. You can also think of that in terms of a tangent plane. It has the same tangent plane when I move along here, or it has the same normal when I move along that edge. Okay? So this is an illustration of case 1, what I want, and this is an illustration of constraint or goal number 2. So going back one step from the bivariate setting, this is a bivariate setting, I go back to the univariate setting and ask the question, but what are we given at the endpoints of a segment or at the endpoints or corner points of a triangle, and how do we get a smooth curved patch in the middle to begin with? Recall 1D case. 1D/univariate case. So we have a domain X. We have per segment, only one segment, one element is of interest. We have 2 sites, 2 locations on the X line, whereas at this point we assume that we have function values plus estimates for the gradient, for the slope, right? And I talked about that, how to get good estimates. And so we could say, well, the slope here is like this, and the slope here is like that. So this is some site x1, it doesn't really matter, x2, this is f1, this is f1 prime, this is f2, and this is f2 prime. And if I have a Bezier curve or a polynomial approximating or interpolating this data, then I need a cubic polynomial because I have 1, 2, 3, 4 pieces of information, so I need a cubic. I need a cubic piece, f of x equals some Bernstein coefficients bi times bi3 of x. Okay. And now I parameterize this in such a way that it's parameterized between 0 and 1. And again, you can always do that. It doesn't matter really in the local setting whether this is shorter than 1 or longer than 1. Locally, you can always reparameterize it as if it was on a unit domain. Later with the triangles, we can do the same thing. So what do we have to do to get these Bezier ordinates? In the middle, you split this domain interval in thirds. Then where are these? And this is a nice relationship between the geometry, the geometrical meaning of these coefficients, and the coefficient themselves. You obtain them by just extending this line, this tangent, there, and you extend this line here, and you get this point, and this would be a split in thirds, 1/3 to 1/3 to 1/3. Then this one is Bezier point B0, this one is Bezier point B1, this one is Bezier point B2, and this one is Bezier point B3. And the control polygon is this polygon. And so you get this cubic curve, interpolating those 4 pieces of information, 4 pieces of 4 data. So this is the unique cubic. Okay. Okay, so now we have the setting in the triangle case where the domain, instead of a line segment, now becomes a triangle. And at the corners, at the endpoints, we have function values plus gradients. So those are vector valued quantities. And we look at that. 2D/bivariate setting. Bivariate setting for just one triangle, for one happy triangle. So what's the situation? Something is given to us at the beginning, something that lives in this space, x, y, and f. And at this point we have a domain triangle and the sides, x, y tuples, with sticks, function values, above them. and gradients. And the gradients, I illustrate them as tangent planes because the gradients do imply a linear polynomial. If I were to render that linear polynomial, I show it as a plane. Okay. So we have the f values, the bullets as before, and we have to give the sides certain names. Now these sides are points with 2 parameters, so I call them boldface, corner 1, corner 2, and here we have corner 3. And we have these gradients. We have f1, f2, f3, and we have, I call them gradients, plus gradients. And I just call them, they are these tuples. They are gi an x component and a g for gradient, a y component, okay? And we have 3 of them for the 3 corners of just that one triangle. Again, I sketch them as little graphs of linear polynomials that might look like this. Okay, that's the situation. And now all one needs to understand is how we take this data from the corners and how do we how we construct the patch, the curved surface in between over that triangle. So what you immediately see is, well, the behavior along the edges. Along the edge here, this probably has to look like that. Along this edge, it looks something like that. Along this edge, it looks like that. So that's the boundary configuration. And, well, now I nearly gave it away. That the first step you have to do is to treat this case as 3 times the univariate case, this one, because you have 3 edges. On the edges, this case is just this case, applied 3 times. So that means along each edge, you have to use these ratios, 1/3, 1/3, 1/3. I no longer talk about a parametrization between 0 and 1. I just talk about ratios now, right? 1/3, 1/3, 1/3. And you have these Bezier ordinates above them. And these Bezier ordinates above them is just this univariate scheme applied to this plane that contains this information. So then I get one Bezier ordinate that lies here, and another one that lies here. And so there is this polygon just for that boundary edge. It looks like this. And there you have the curve case. Okay? One Bezier ordinate, another one. And these guys live at these locations. 1/3, 1/3, 1/3. And you do this construction for the other 2 boundary curves as well. I don't want to draw it because if I drew it, then you wouldn't see it anymore. But the patch is not an empty patch. It's not hollow in the middle. It's really a surface, right? So, I mean, I'm just talking about the 3 edges. That's the wireframe model. We want more than that. We also want the stuff in the interior, right? It must be solid. Well, there's something there. So how do we get actually the stuff in between if we just have the boundary information? So first observation is we simply apply the 1D case. This is colloquial, of course. Apply the 1D case 3 times for the 3 edges. Apply the 1D case / construction 3 times. 3 times. For each of the 3 edges. This also has a name, this construction. How many pieces of information are there? 1, 2, 3 function values plus 3 times 2. Okay, so there is 9 pieces of information. That's the way to think about it. So that's why this thing is called the 9-parameter cubic. A 9-parameter cubic. 9-parameter cubic patch. Again, why? Because this is the input that's feeding the construction. What else? So where are we now? We need to determine the Bernstein ordinates. Need to determine the Bernstein ordinates. Slash control points P and PS. So let's do that just for 1, and you will see how that works. Side, and side, triangle. Okay, let's just look at this corner, C1, C2, and so I split this edge into thirds, so 1/3 to 1/3 to 1/3, and I want the 4 control coefficients, the 4 ordinates for this particular curve along this edge. So say this is the implied shape implied by the gradient information, and this means that a control point must lie here somehow. The control point here must lie here, and here's my control polygon for just that one boundary edge. And we only have to understand how we get one of these circles. If we understand how to get one of these circles, we can do the same, can play the same game for all the edges. So what are the control points? Let's remember what the scheme is, the numbering. I'm now looking down from the top. If it's a cubic patch splits all the edges in thirds. So this is a top-down view on the structure for which I need the Bezier points. So this guy would be Bezier point B300. This one would be B210. This is B120. This one is B030. This guy is B003. And then this one is B021. This one is B012. This guy would be B201. This one is B102. And there's a happy guy in the middle, and we come back to that later. How do I get this Bezier point here? This Bezier point is B300. And this Bezier point here is B210. This is an abstract view. This is the way you store it in your array or whatever, triple index. And here's the geometry. So here was a function value. Here you have a function value of 1. And you also have your tangent plane here, right? Right, there's the tangent plane. All right, so how do you get this point, B210? How do you get this one? That's all you need to understand. Then you can get all these circles. If you know how to get one of these circles, then you know how to get all the circles. So first, the corner value there is, of course, a given function value there, right? But then this guy, how do I get that guy? Here's the 1D. Here's the 1D construction. How do I get the height for this circle ordinate? I take the tangent or the derivative, the slope, and I extend it up to a location when I'm 1/3 along this segment, this line segment. Here's the same thing. Here I take the direction. This tangent plane also has a direction in the directed line segment from C1 to C2. And this point is 1/3 down the way. So therefore, I just evaluate this linear polynomial. There's a linear polynomial there, right? A polynomial that defines a plane. I evaluate that plane at this location. I evaluate this particular linear polynomial, this line, at this location to get that circle. So I do the same thing. So here, the tangent plane, let's say that in words here, the gradient at C1 implies a linear polynomial, a linear Taylor expansion at that point. It defines a linear Taylor expansion of the form, I just call it L for linear, L1, 1 for corner 1, and this thing is a function of xy, and it will be a plus bx plus cy of that form. But then the a part is the function value there. It's f1 plus, and the derivative is, what is it? That is the gradient, right? Did I call it, where did I say? Index I is the lower one. Okay, so this is gradient 1, the x component, times x minus x1 plus the slope in y direction y minus y1. This is a linear function, a linear polynomial of the form a plus bx plus cy when you multiply it out, which passes through this function value and has this gradient. When you differentiate it, you get this gx and gy as gradient. Okay, so now this function xy, you can evaluate it anywhere. Particularly, you can evaluate it there and there. Well, actually, you only need to evaluate it there and there to get these two guys from that corner. So you get b 2 1 0. I forget to make these commas, but know that they are commas. So this thing is just the Taylor expansion L1 evaluated at this particular location here, at this particular location, P. Let's call this guy location P. And if this is 1/3 down the way, then P is what? P is 2/3 of corner 1 plus 1/3 corner 2. It's just linear interpolation along that edge. So then you evaluate this linear polynomial L, this tangent plane, if you think of it geometrically, at this location P, and you get the height there, and that height is its ordinate, that coefficient. L1 at point P. Okay, that's all you need to understand. How to get a corner value, you play this game 3 times, and how to get a circle. Right? And you play the circle game 6 times. 1, 2, 1, 2, 1, 2, 2 for each edge, and then you have nearly all the points except the guy in the middle. Okay. I mean, correspondingly, you have another Taylor polynomial here. Here you have L2, and here you will have another linear function, right? A linear function L3. The functions defining these planes there. Okay. So what comes next? Well, next we have to worry about this guy in the middle. Right? How do we choose that one in the middle? Obviously, it's a necessary coefficient for this strange barycentric way to represent the triangular patch. But also need a good value for, well, this point in the middle is B1, 1, 1, right? B1, 1, 1. B1, 1, 1 is a control point in the middle. This guy. Now you can think it's a sculptor, right? Like a sculptor. You're sculpting this. It's a piece of clay. You shape things. So what do we have? We have some beginning like this here, another big ending there, and the beginning here. And you would like to use your hands to smooth this, right? Kind of like blend this together smoothly. So if you want a smooth variation of your tangent plane from this corner point and this behavior to this corner point and that behavior, there would be maybe a linear variation, how you change that, right? When you go forward and backward. So this variation along that edge would imply a value for star. In the same way, if you want to have a smooth variation of the tangent plane behavior here, that would imply a different value for star. If you were to do the principle here and have a smooth variation of your tangent plane at this curve, it would imply another value, a third value for star. These three values for star would be different, so there's a conflict. Okay, so there is not the best way to choose this degree of freedom in the middle. So again, people have just said, okay, principle is this. Principle goes back to this polynomial precision. If I knew, in the 1D case, that all my samples originate from a nice, beautiful quadratic function, then I always want to make sure that if I have these samples, that the output I produce is exactly that function. Okay? Polynomial precision. And one can also force this B111 to reproduce quadratic functions. So if all my sample points above the plane come from one unique, globally unique quadratic function, I want to reproduce that. And based on that assumption, if I want to enforce that, then there is a formula coming out for B11. And just read the Farren book. See Farren book on quadratic precision. Quadratic precision. Quadratic precision of 9-parameter cubic then ultimately when you force that, you get the construction and the condition for B11. Then B11 has to be 3/2 times B minus 1/2 times C, where B is something and C is something, where B is the average of all the circles, B is 1/6 of the sum of all the circles. Okay, you can put the actual B values there, but I just say the circles. There are 6 of them, so it's the average of those. And it's the C is the average of all the corner values, sum of the Bezier coordinates at the corners. Okay. So I just say this is 1/6 of B210 plus B120 plus blah, blah, blah. And this guy is 1/3 of B300 plus B030 plus the last guy. Okay. And so in a sense, this is an optimal setting for B111. So now you go back to the original goal that we have in mind. The original goal is to construct an overall shape that is smooth. When we illuminate it, we want to have a normal vector that is continuous, right? You can think of it in terms of computer graphics. You do not want to see ridges. No? You do not want to see Nachbarn defects. No? You do not want to see the edges of the underlying triangle mesh. You can ensure that by enforcing that the normal along all these edges of these triangular pieces is the same, is continuous, right? Okay. We need to have that property satisfied around the shared vertex, where multiple patches go around a shared common vertex, the degenerate vertex. And the other condition, we want to ensure this normal property is along the edge, right? We want to have one and the same normal, where two patches come together. Is this the case? We have to ask ourselves now whether this construction, the way it's on the board, makes sure that we have the same normal for all the patches coming together around this corner, and whether we have the same normal along this edge between this patch here and its neighbor down here. Huh? Those are the two conditions we want. We want to have that this configuration. We have 3 patches coming together there, 3 or 4 or 5 or 6 patches, and we want to have one unique normal there for illumination, say. And we want to have the shared normal behavior along the edge, the cross boundary, right? So this should also have the same normal. Is this ensured and is this ensured by this construction on the board? Let's do the one that's easier. The easier one is in fact the one where you look at the degenerate point, the singular vertex, the corner, that's shared by any number of patches, right? Again, also make sure that there can be an arbitrary number of triangles coming together, right? This is unlimited, right? This situation, multiple triangles come together. Is this construction guaranteeing that when all these patches come together, there's one unique normal? Yes. Jennifer? Yes?
Yeah, it would be because assuming that you calculated the gradients initially based on the points around it, and if you just take the normal to be the normal of the gradient plane, it should be the same.
Indeed. Good argument, correct. Because you use the same linear polynomial, right, for the construction of all the triangular patches coming together in this neighborhood. So when you just look at this guy, where all these things come together, you have, say, I don't draw too many, say, 5 triangles coming together. And when you construct this next level or this next layer of control points, you use indeed the same linear polynomial to get all these guys, these circles, right? All these guys live on the same plane, on the same linear polynomial, so therefore there will ultimately be one gradient or one normal on the surface of the thing. So that's assured. But then the other issue, I said that was easy, then this one is probably not so easy. So here we have the same normal assured at the corner, right? Here we have the same normal, here we have the same normal. But when you traverse along the edge, ugly things can happen. Namely that in the middle, the normal for the left patch goes there, and when you evaluate the right patch, the normal goes there. You can deviate. It's bad. All right. But, another but, and this is a big but, two neighboring triangular patches or just triangles, two neighboring triangles do not necessarily share a continuous share the same gradient along the shared edge. So yes, they share the same locus, the same geometry, the same edge itself, as a curve in space, but the normal along that edge is a different one based on whether I'm coming from the left or whether I'm coming from the right. Okay, this is not good. Condition for a continuous gradient along the edge of two neighbor triangles, for continuous gradient grad along edge, along shared edge, and I just sketch that, so and then I will stop. So there is this shared edge, two endpoints, and so there is this polygon, just defining the geometry of the edge itself, and then there are these two triangle pieces. There's this one triangle to the left, and there's this other triangle to the right. Right? So a left, call it left, and call it right. And so this is a depiction in XYF space. XYF. And now you want a cross-derivative continuity. And that condition translates into a condition of coplanarity or linearity of certain things, namely these things. Okay. There are these quadrilaterals, which are two layers, which are two layers, one to the left and one to the right of these control meshes, control polygons, and these points in these quadrilaterals have to be on the same linear polynomial. These four ordinates or points have to belong to the same linear polynomial, i.e. it has to be a planar quadrilateral. These guys, these four guys, have to lie in the same plane, and these four guys have to lie in the same plane. If that's not the case, then there is a gradient discontinuity. And so again, these two triangles forming a quadrilateral in union have to define a planar quadrilateral. These guys do that, satisfy that by condition, by construction. At the corner points, we have that built in, that these guys indeed will lie in a plane, will lie on one linear polynomial, but these two triangles are not necessarily lying in the same plane. So this quadrilateral, this quad, must be a linear quad. Must be defined by a unique linear polynomial, linear poly. Bam, bam, bam. And then you can prove that, etc., etc. Again, these two triangles lie in the same plane by construction. These two triangles lie in the same plane by construction. These two triangles do not. In a top-down view of the situation, when you think of it abstractly, there are two triangular patches coming together, right? And then they are cubic, two cubic patches, and so they're corners, and the associated ordinates, I use this bullet notation, and then since it's cubics, the edges are split into thirds, then the control mesh looks like this. Okay, and so these are the corner-induced, the corner-dictated circle values, And then these guys, we use this magic to compute a B11 for them. But these 4 points do not necessarily lie in a plane or do not belong to the same linear polynomial. So that's where the problem arises, this situation. So that means when you render these two triangular patches coming together, the more you approach the midpoint along the shared edge, the more you will see a ridge. There will be a ridge, a visible ridge, because the normals point in different directions, right? Unless the overall shape from which these samples come was one unique quadratic polynomial, f of xy equals x squared plus y squared, then there is no edge because you can reproduce it. Okay, so there is a problem with it, and we don't like that. So therefore, there is another approach of handling this problem. Well, namely by avoiding it altogether. And this relates to so-called split schemes, splitting. Let's use splitting to completely avoid this problem, to avoid this problem. I have not talked about splitting, the general approach about splitting a bigger problem into a smaller problem at all, so I should first talk about it in the context of the 1D case. 1D case example for splitting of splitting. Splitting or subdivision. We go back to our problem, namely we have two function values at the corners and two derivatives. Two FCT and two derivatives given. Derivs given. So this is the setting, a line, a side, a value, another side and a value. And now I don't even number these things, and I do not even fool around with indices. I just show the construction. So we have the sticks and we have derivatives indicated by slopes, as these little line segments. And I want to interpolate to that data. So I want to get, I know what I want to get a shape like that, right? That's the desired output. And I can do that with a unique cubic, with one cubic. And now the idea of splitting says I split the problem into two simpler problems. How do I do that? So I split everything into two. Okay, I split the domain into two subdomains by splitting it into a left chunk and a right chunk. And I will split the overall curve that I want to get into two curves that I will construct. Instead of constructing one curve, I will construct one composite curve that will consist of a left piece and a right piece. And the pieces in union will give the overall result. That's the idea. So I only deal with the information on the left, the information on the right, get a partial result on the left, a partial result for the right, and then I take the union of that. That's the splitting approach. Take the problem, make it simpler, construct partial results, and then merge them. Okay. So now I only have the problem of I have to interpolate to a value and a derivative. I could do that in principle by a line already, but I use a quadratic. They have some smoothness in there. You will see why I do that. So I have a thinner line here that I put here. And if this is a quadratic polynomial, well, it has to extend like that. Okay. I do the same thing on the right portion. So this is my left part, left, and here's the right portion. Again, if this thing should end like that with this tangent, then it has to have a control point there, if it's a quadratic. And now comes the trick. Well, of course, if I merge these things with a straight line, then everything is smooth and continuous, also at this midline. And I have now a quadratic piece on the left, which looks like this. And I have another quadratic piece that looks like that. And I have reduced the problem from constructing one cubic polynomial to the problem of constructing two quadratic polynomials that also interpolate the data, right? The left quadratic interpolates to the stick and the slope. The right quadratic interpolates to the stick and the slope. And by construction, I'm forcing these two quadratic arches, these parabolae, to come together in a continuous way. By forcing this point here, this square, to lie on the line connecting circle and circle. So then I have a first or left quadratic piece. And here I have a second quadratic piece. Second quadratic. And so, again, given was this value, f1, and the slope 1, f1 prime, and the function value 2, and the slope, function value 2 prime. And I constructed these 5 Bezier points. This one, this circle implied by the slope, this one, this circle implied by the slope, and then this guy in the middle is merely constructed or implied by forcing the square to line on the line segment from circle to circle. And then I get automatically a composite curve that will interpolate to the given data at the end, and also will have a smooth breakpoint in the middle. This is also nice because now I no longer have to deal with cubic output but with quadratic output. In computer graphics, you already know that dealing with lower degree polynomials is always beneficial because then you have ultimately square roots to deal with that you can solve, right? Okay, so this is the idea of splitting. Idea was instead of using one cubic, we use two quadratics to interpolate the given data at the endpoints. To interpolate the endpoint data. So one can use the same principle, of course, also for triangles or triangular patches. And there exist many split schemes for triangular approximants. And one of the most important ones is the clough-toucher split. Which splits our given problem. No, it doesn't split the problem. Which solves our problem. which solves our triangular patch problem. By splitting a domain triangle into 3 children or child triangles. Is everyone with me so far still? BC, you're with me, right?
I actually had a question back there, because I'm still trying to figure out the motivation of this. I understand how we could break it in pieces, but why is that polygon in the background where you have those striations not being touched? And what's an example of that? You said that that's the problem that creates this solution.
Which of the points is a point in question?
So, the triangle with stripe, or the polygon with stripes, you said that that isn't abutting or touching the surface, correct?
When I illustrate this as a three-dimensional picture, x, y, and f, and the control ordinates, or these coefficients, come out of the board, then these quadrilaterals should be planar quadrilaterals. So in this particular situation, these two guys would look like this. And one would have a normal like that, the other one would have a normal like that. And this would be the shaded region there. This is just this part drawn as a three-dimensional surface. These guys should be coplanar. But in general, these two triangles will not lie in the plane. And the fact that these two guys are not in the plane will imply the fact that the normal, when I evaluate this edge, will be different. Yeah, well, this thing doesn't have enough degrees of freedom. Yeah? Because you have conflicting continuity conditions that all try to influence the choice of this point in the middle, namely 3. This point in the middle is influenced by the behavior of normals along 3 edges. And it cannot satisfy at the same time the normal behavior of all 3 edges, but just one. So if I were to enforce this guy to be coplanar with that one, at the same time I would then ruin the coplanarity constraint with these other two neighbors. I can never guarantee now that all of these things are coplanar. I cannot get there. So therefore, that is not a good scheme. It is good enough for many purposes, but not ours. I hope that helped a little bit. You see, did it help a little bit? How do we split? Should make a picture. Should I do a picture in the domain or first in 3 space? Let me do illustration in 3 space. I tried to x, y, z. We have more and more information now because we split things. So the resulting patch now is a mega patch. This is a big patch, but this will be the result of compositing or combining 3 patches. Okay, so here's my original domain. Triangle, and over this original domain triangle, I construct 3 triangles. And each one, that's what clough-toucher does, each one of those will be a cubic one. Okay? So this was an original corner corner 1. This is an original corner, corner 2. This is an original corner 3, C3. But then, because we have this ugly problem over there and cannot solve it just with one triangle over this domain triangle, we know we need to split it. That's what we do. And we split it by just taking the centroid of the 3 corners, okay? And then construct 3 child triangles, triangular patches, over that split. Okay, so this one will be a cubic polynomial in its own right. Huh? This boundary curve will be a cubic boundary curve in its own right. This curve will be a cubic boundary curve in its own right. And there is one little heavy point in the middle. Okay, so I'm just alluding to these 10 control points. For this patch, there will be 10 control points for that patch, and there will be 10 control points for that patch. So then the question is, how do we now get the control points for these 3 mini triangles? Is this more difficult to compute, or is this more easily computed? Is there any degree of freedom? Freedom is good, because then you can choose. Not having enough freedom is bad, or being over-constrained is really bad, because then there's not even a good choice, right? So this is too many constraints, you cannot even achieve what you want. Here, will it be overdetermined or underdetermined a problem, ultimately, to pick all the values for all these control points? It would be great if we had just enough degrees of freedom as we have pieces of input data, right? It would be great if they're just, right, is perfectly matched. And it happens that this clough-toucher scheme perfectly matches the data we have at the corners, namely the function values and these tangent planes, with all the degrees of freedom we have. Perfectly. There is not 1 degree of freedom missing, nor is there 1 degree of freedom too much. Just matches. And so now I can sketch this schematically, in an abstract way, the way you would store it in your computer, in your data structure. And I can no longer draw this in 3D, but I have to sketch it by looking down onto the structure. The structure and construction. Structure and construction. How do I do that? Okay, I just put a big triangle here. So this is the mega triangle, the parent triangle. And we have to follow our intuition, because our intuition is usually pretty good, right? At this stage, we are fairly advanced computer graphics experts, and we can trust our intuition. So the first way to deal with this problem is we compute the centroid, the center of these 3 corner points, and declare that a new point here. The point lives here, and we call it square. Okay, so now we have, and again, I'm looking down into this configuration into the xy space. So all the ordinate values, these sticks are coming out of the board. We have this geometrical connectivity. Now these are cubic polynomials living above those. So for each one we need 10 control points, and each edge is split into 1/3. So I have to do that now. I split all these edges into 1/3. 1/3, 1/3, 1/3, but I, as good as I can do that, standing so close to the board. Okay. Now the control point structure then will look like this. Dup, 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 dup. Right, that's 1 cubic with its 10 control points. Then I have one here. Dup, Tup. 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 And tup. Tup. And so here's the boundary between those two patches coming together, right? There are two curved patches living above this domain. Another one is here. Okay. Okay, that's a structure. All right. And now we have to compute values for all these vertices in this mesh, right, in this structure. What are the coordinates at the corner values? Right, this is corner value 1. What is that?
Sorry.
Cell phone?
Yeah.
Just tell them, I call them later. So these are the corners, and at the corners we have Bezier points. What are they? The given function values, right? At this corner, just to provide the context, that's where we have our original function values, right? F1 and F2 and F3 and all of that. At these points, of course, the Bezier coordinate is, so here we have locations, right? Locations or points, locations. And at the locations, we need certain ordinates. The ordinates are coming out of the board. Those are the values of this control mesh. So the values of the Bezier or Bernstein coefficients, coefs, B, I, J, K, at the corners is the given function value, right? We know that. At the corners is the given FCT values. Okay, that's easy. That's case number 1. The next case is the next ring or the next layer of values which we call circles, right? These are the circle values. So, and we have these circles all over the place, namely around all the corners here. Okay. How are they implied? The values of these ordinates. Here's a linear polynomial, that plane living here. So these linear polynomials imply the height, the sticks for the circles, right? So we can say all the circle values are implied by the linear polynomials or the linear Taylor expansions at the corners. So all of these guys are implied by the linear polynomials, linear corner polynomials, which are in turn are implied by the gradients, polynomials / gradients, grads. Okay. Now what? There's too many degrees of freedom left, right? I said we don't, now we have even more degrees of freedom to choose, all the stuff in the middle. Is it really free or not? I think that this is the real trick of this clough-toucher scheme. So again, this mega triangle, this parent triangle, has 3 neighbors, right? It has a neighbor here, it has a neighbor here, and it has a neighbor there. And there are these 3 boundary curves living above these edges, right? And we want these surfaces coming together in a smooth way, here, here, and here, correct? So therefore, there is probably something with this guy that has to be satisfied, because this guy is the star over there. So we want this triangle, this big mega triangle, to be smoothly connected to that guy, this guy to be smoothly connected with this neighbor triangle, and this guy to be smoothly connected with that neighbor triangle there, right? Okay. Therefore, you can enforce this coplanarity now, or this linearity constraint, for these guys, by making these values associated with this location to be the average of these 2 values. Okay, that's the trick. Okay, the value here, the ordinates coming out of the board here, is the midpoint or the mid value or the average between the value here and the value here. Same here. The value here will be the average between these two values, 2 sticks coming out here. And here we have the same construction. We force the value at this location to be the average of those two circles. Okay? By doing that, by forcing it this way, we will later on make sure that the value we construct here will indeed be leading to a linear configuration for these 4 points. So that's all I would say. I say this is a value, let me call this value A. I have to give it names. Value A and B. Then the value at this location is merely 1/2 of A plus B. This location value is 1/2 of A plus B. To just allude to the fact that these values in the middle are the averages of their line neighbors. Okay, now what? We still have 1, 2, 3, 4 degrees of freedom, right? Are they really free or are they implied? These 3 mini patches or child patches, of course, should come together in a smooth fashion in the middle, right? Right? There are 3 little pieces coming together. They must themselves be coming together smoothly along these edges and around the shared vertex in the middle. Is there any freedom left or not? No, there is not. Because now you have this triangle and this triangle, and these 4 points have to lie in a plane, have to lie in a linear polynomial. Point 1, point 2, point 3, and this guy, point 4. These guys, with this guy, have to define a plane. So the triangle has to lie in the plane that is already implied by circle and 2 stars. So triangle is implied. But then this triangle is also implied because this triangle value has to lie in the plane of these 2 stars in that circle. Then this triangle guy also is not free, has to lie in the plane or on the linear polynomial between these 2 stars in that circle. Okay? Okay, so I have to say the location is a triangle, and the value there lies in the linear polynomial implied by the 2 stars and the 1 circle closest to that triangle. Okay, value here must lie on the graph of the linear polynomial, on linear poly, implied by 2 star points and 1 circle. Okay, all right. But now we have still 1 degree of freedom left, namely the guy in the middle, right, where the 3 pieces come together. Is this free or not? Just follow your intuition. At this point, we have constructed everything, right, from the corner, and we walk inwards. But this is the last free piece. Is it free or not? The closest things to this guy are the 3 triangles, right? There are 3 sticks coming out here. These sticks imply what? 1 line, 1 plane, 1 linear polynomial. And your intuition tells you that in order for all the 3 pieces to come together in a smooth way, this guy probably has to lie in that plane implied by these 3 triangle values. So it's not free, it's implied. So this is the value at the point in the middle. Is indeed, turns out, it's the average, right? Or can say it lies in the linear polynomial implied by the 3 triangles. Value here lies on the linear polynomial, on linear poly, defined by 3 triangles. Okay. So what do we have as a result? As a result, we have a nice, beautiful triangular patch, right? Which is a composite of 3 baby patches but you don't see that there are edges at all. Very smooth. When you're in it, there's a continuously varying normal gradient throughout. And, of course, this construction will also ensure that when you apply the same construction to the next mega triangle, to any of the shared neighbor edges, you will also have a smoothly varying gradient and therefore a smoothly varying normal for shading along these shared edges. Okay? This is beautiful. Why is this beautiful? You had a fixed amount of information given, 3 sticks and 3 planes, and you have just the perfect number of polynomial coefficients that you need to interpolate exactly to all that information. And everything is as smooth as you want it to be, namely C1 continuous. Okay? The gradient is smooth everywhere. So when you render this type of terrain or interpolated terrain data, you don't see ridges, it's smooth, and there are no Machband effects. And so on. That's good. Now, next time we have to talk about 2 aspects, and then I will start talking about Warner diagrams. So these were cubic pieces. Are cubic polynomials good? In the motivation, when I talked about splitting in the first case, I reduced the cubic polynomial to 2 quadratic ones, right? And I also said that's good because quadratic pieces lead to square roots that you can solve, right? That's good. So therefore, maybe there's also a way to deal with this problem by using quadratic pieces and not cubic pieces. Again, there are major advantages for simulation, lower degree, better stability, and less error, blah, blah, blah. For us in graphics, it means ray tracing is possible, and ray casting and contouring is possible when we have to deal with roots that are quadratic roots, square roots. That's good. The other issue is, okay, this was a construction for surfaces, right? We have scattered data over the plane, height values, like terrain data, right? The problem I talked about is really terrain data, height field data, right? You have a bunch of longitude, latitude, location, and you have height, and you want to reconstruct the Sierra Nevada as a smooth function, right? You can do that. But we want to do this for temperatures in the room. So I also have to talk about how to do this when we actually have to split simplices, right? So the triangle will become a tetrahedron, and instead of splitting using this particular scheme, instead of splitting a triangle into 3 child triangles, the generalization would be splitting a tet into 4 child tets. Okay, cubic ones. That's one. And so next time is splitting with quadratic elements, splitting in the volumetric case, and I will begin talking about Warner diagrams. Thank you.